Hello, how was your weekend? Uh, Week number 8, and just past half of the semester, right? I'm gonna talk a little bit again about what you already submitted. I'll cover 2 chapters, and I will inform you that I made a little bit of a change. We didn't have a synchronous meeting this week, but since they changed the advising period, I had to move it. So this week we're going to have a synchronous meeting. Again, extra credit and the whole thing per use. So I'm going to remind you at the end, but I'm just saying it right up front so I don't forget. It's this Wednesday at 10. Okay. So feedback about what you submitted, and I'll start with LO12, 89%. I have my notes right here. There was an item that I want to address about IACUC, how many practicing vets, and the answer is on page 225, 225. So if you go there, you'll see, excuse me, how many. LO13, 86%. I have again one item to address, and that is about the grant review panel and how they evaluate the proposal. So if you go to page 249, 249, you'll definitely find the answer. If for any reason you can't find it or you want to talk about it, office hours tomorrow from 8 to 12:30, synchronous meeting on Wednesday, or just shoot me an email, okay? So I'm going to go ahead and share our Moodle site. All right, here we go. So as I said, week 8. So right here, we have the city group training, which is an extra thing you have to do for this week, for this Sunday. Okay, again, submit the link or the certification of completion through Moodle. These are the guidelines. You don't have to pay anything. You create an account through Plattsburgh. Okay, so this is for this Sunday. 1. So what else do we have? We have LO14 and LO15. Okay, and also, as I said, a synchronous meeting this Wednesday at 10 o'clock. Okay, switching it up a little bit to make it a little bit more fair. So at 10 o'clock. Cool. All right. That's pretty much it for what we have. And yeah, I'm just gonna go ahead and share the first PowerPoint slideshow. Stop sharing this. And I'm just gonna go ahead and cover what we have for this week. Okay, we have 2 chapters. I find this chapter, although a little bit shorter, more interesting, more applicable, especially towards your project. As you go towards this, please think about what you're thinking about doing, and you may even do a pilot study. Who knows, right? If that's what you want. Okay. All right. So at this point, we are right here. Okay. This is what we're gonna talk about today. Some key terms. We're gonna go over some pretty interesting stuff again, especially as you are preparing your mock proposal. The other chapter we'll have for today is equally important. It just, in my opinion, it goes into a little bit too much detail, so we'll figure it out as we go. All right, so remove my face. So you want to do a study, right? So you need to figure out the characteristics of the sample. So what kind of people are you going to recruit and why, of course, right? In general, we want, of course, as it says here, the sample to be representative of the population. Why? Because then we can extrapolate, okay? And also, as you can see, there are inclusion and exclusion criteria. So in your study, you may have only men or only women or children or athletes or people with cardiovascular disease or chronic illness and disease or whatever, who knows, right? So you are going to determine the characteristics of this study, okay? So this is important. So again, as you're reading this chapter, watching this video, put some notes down, try to think about what you want to do and why, okay? All right. So there are pros and cons. Would it be great, like if it was possible and we can just examine everybody? Like in terms of power, sure, because you just have everybody. So yeah. So the larger the sample, the more power. We're going to talk about power in a little bit. You get, so that's wonderful, right? But it's more difficult, and in terms of time and money, as you can see, but also maybe unethical, because if we figure out that we need a blood sample from 100 people, and you recruit 1,000, so why did you even put these people through these 900 people through that? Okay. And it can also be unethical if you have a very small sample. So if we do need 100 people and you do the study with 10 people, so pretty much you have nothing because you don't have power. So you made those 10 people to go through something that was completely unnecessary, right? So again, as you can see, there is a type of there's a specific kind of thinking that you have to do here, and you need to understand that on one side we have less data, on the other side we need more resources, okay? Now, how are you going to determine the sample size? And that really goes into your proposal. Maybe you need to do a pilot study. Maybe somebody else has done the pilot study and they have determined the sample size. Or maybe you go into the literature and you just follow whatever everybody does if your thing is very similar to their thing. Or as you can see, like that data can come from your own lab or from somebody else's lab or work in general, right? And we've talked about confidence interval, we talked about variability in the past, but also we can use software, right? And so there are several ways to do it, and there are several different software. But for this class, I hope you've seen it. We talked about a little bit about it a little bit. You can use G-Power. So the G-Power software is free, and it's pretty easy-ish to use. So I would start playing a little bit, and I have already given you a whole PDF, or I've told you where it is, so you can download it and read some instructions up to the point that you need for this specific project. And it's time for you to start thinking about that. Okay. All right. So determining the sample size, and you'll see if you use G power, you have to think about three things for sure, right? I'll start with the alpha level that you've seen, I'm guessing, before, the p-value, right? And typically it's, as you can see here, it's set at 0.05. And in a very simple terms, it means that we're sure, if everything goes well, we're sure like by 95% that whatever we got is not random. So that's the statistical significance. So when we talk about statistical significance, we need to use that alpha. We're usually using that alpha level, right? We make those comparisons, and most likely in G power, you'll put the alpha level at 0.05, okay? If it was 0.01, it would be different, for example. So there's sometimes it is different, but that's what we typically do. All right, so then we have the effect size. As you can see, expected difference between the null hypothesis and alternative hypothesis. Okay, so here we're trying to figure out if we're looking for some practical significance, and that's where the effect size is helping us. So what is the difference between those two hypotheses, those two different scenarios that we're talking about? Okay, and the power is, as you can see, the probability that the selected research method is able to detect a significant difference when a real difference exists. So usually it's about 0.8. So if you have really strong power, that means that there's a high probability that the method that you chose will detect statistical significance when there is actually a real significance. So it will detect something based on the alpha level when there's something on the effect size. Okay, if your study is underpowered, then that's not good because the probability is really low. So whatever you want to say based on your results, does it really matter when the probability of your method to be able to detect that significant difference, to detect a significant difference when a real difference exists is really low? Does it really matter? So these are the three things that you will need to put in, most likely like an effect size of 0.5, alpha level 0.05, study power, the power 0.8, and see what sample size you get based on that. Now, different fields may require different numbers, okay? This is not something that is set in stone. I just want you to at least understand that what is a statistical significance, what is a real difference, like practical significance, and that how power kind of brings those two together, okay? All right, so in general, when we are trying to find the sample, there are different methods. One way to group those are between probability and non-probability, okay? And if we use probability, we'll have lower bias. And I'm sure you know by now that that's good. That's a good. Lower bias is always something we're looking for. Now, it can be simple, systemic, or stratified. Simple can be, and our book gives a great example. You can just have some random piece of paper on a table with numbers and just people come and get one. In general, as you can see when we're using probability, the fact that we're choosing one person does not change the probability of another person to be selected, or the chance. Okay, so everybody has the equal chance. It is completely random, right? So we can do it through a simple method, a systemic method. So we send out invitations, and every fifth received or fourth or third, we accept that person. It's just a method. It's systemic, so it's always the same. It's random, right? We just send them out everywhere. And it can be stratified. So you can have some subgroups in your sample, right? So stratified based on age, based on level of cardiorespiratory fitness, based on whether they're athletes or non-athletes, okay? But still random, okay? It's still random. It's just you are interested in some specific characteristics and you stratify that way. That's the study something, the random numbers at the table. And this is a non-probability. Does it happen? Yes. Does it happen often? Yes, also yes. So here, not everybody has the same probability of being selected, okay? And I'm guilty too, and I've used a lot of times convenience sample. And in terms of bias, it's not good, because if I select you, all of you, in a whatever project I want to do, research project, so we do that all the time, and or my team, just my team. So that's something that I'm using because it is convenient. It is not random. So whatever results I get, how am I going to be sure to extrapolate? And that's the big thing. We covered it already, right? How can I go from the sample to the population? I can't, because it's just a convenient sample. It's not representative of the population. It was never representative of the population. Okay? But sometimes that's what we have to do, and that's limitation of the study. Right? We also have the comparative effectiveness trial, where we compare usually something that we already know with something new. Again, it's a non-probability method. Pilot testing. So we have a project, we are ready to do it, but we need to practice a little bit and make sure we have everything covered. So we make sure that time-wise, how much time it takes, if everybody's educated, if we know how to use all the equipment, if the equipment is right, calibrated, and we're going to talk about calibration in a little bit. So pilot testing is great, and it gives us a lot of information, and we can tweak stuff in our method if we find something, or we can just keep practicing. So if we get a lot of measurement error, because as researchers we weren't uh, haven't practiced enough to collect the data, then maybe we the big takeaway from that pilot testing is that we need more education. We practice before we start the actual thing, and this is great, right? Because it saves us from a lot of pain later on. These are the things here, as you can see: assess measurement variability, practice methods, develop instructions for data collection, examine feasibility of methods, familiarization needed for subjects, and data to estimate sample size. That's another big, which I forgot. A lot of times we can run some stats based on what we get, and that may help us figure out how many people we need. That's why we need sometimes that pilot testing, that pilot study. Right? Sometimes we don't have enough data. We don't know. We don't. So, and I've done it, and I'm doing it right now, actually. I'm doing pilot studies for many, many reasons, and that's one of them. Can I get enough power with 10 people? I don't know yet. So I'm doing a pilot study, and I'm trying to collect all that other information, but also I'm trying to collect information about the size of the sample. All right. Collection of the data can be affected by many reasons. We need to figure out attrition, and attrition is that thing that you see about dropping out. So that's another big one. You can get a number from G power, right? You'll get like 40. You need most likely to add some more people because of attrition. How many? I don't know. Look in the literature. Maybe 10% is something you expect. 20% is something you expect. If you're expecting 20% and you go to 48, you'll go for 50. Okay. And again, if you justify it, it's fine, right? G power gave me a minimum of 40. I'll go to 50 because of that. You can go to 140 though. That, you know, so that's one way to justify to me in your project why you're choosing this many. Okay. Yeah, nothing really. Okay. I hope this was a little bit helpful for your project. So now I'm going to go ahead and talk about chapter 15. And again, chapter 15 is a little bit longer, and in my opinion, it goes into a little bit way more detail. So I'm not going to necessarily stay in everything like for a long period of time. I'm just letting you know. Okay, so let's see what we have. Sharing our screen. Right here. Okay. All right. Well, so here again, we are talking about data collection that can happen right here or right here, but you'll see it's this is kind of especially the beginning of it. It's important for you to understand how to collect data and how to interpret data in general. Um, so and in terms of error, calibration is huge. So let's see what's up. A lot of terminology, don't freak out. Explain most of it right now, but everything is in the book. Okay. We're starting with a definition. Measurement is a systematic and replicable process by which physical and non-physical phenomena are quantified. So quantification. So we need hard data. We need some kind of numbers. I need something to measure it. Okay. It is systematic, so there's a system behind it. There's a systematic process and also replicable. So you'll see when the time comes and you write a manuscript and you want to publish, the whole thing is reproducibility. Got it. So you need to explain to everybody what you did. So if they want to do it, they would know what to do. And if you did everything right, they would get pretty much the same results. So this is about measurement is huge. Okay, so we talked about the method of the whole thing, but then when we're actually trying to apply it, the method of the whole thing is very important, obviously, but we need to be able to go through this process with as few errors as possible, and we'll see why. Okay, so I don't like these definitions. We talked about that before. Reliables are not the measurements. They're not the techniques. Reliability has to do with scores. Okay, so reliability has to do, it's reliable are scores of whatever. Okay, you're using scale, that weight, that number that you got, that is reliable, not the scale. Okay, and validity has to do with the inferences that you make based on those scores. You cannot have validity without reliability, right? You can have reliability without validity. It happens a lot, actually. So yeah, okay, all this is great, but I would also like you to remember that scores are reliable and inferences are valid or not, okay? Tools are not reliable. All right, so interclass correlation. So here, we make measurements of whatever, the same quantity, and we're trying to compare and contrast. That's what it is. It's about, again, reproducibility, okay? The coefficient of variation is, it tells about if we have the same quantity of whatever, when we measure it again and again and again, how much this measurement varies around the mean, okay? So these are two ways to figure out if the scores are reliable, okay? So how much varies around the mean, and also you get two scores of the same thing, whatever you're measuring, and you compare them, the same quantity, okay? Technical error of measurement, it has to do with something that has most likely do with the apparatus you're using, okay? The minimal detectable change is you're using something, how much of a change can it detect? 0.2 milliliters per second? 0.1 milliliters per second. And that is important if you really think about it with a minimal worthwhile effect. So how much of a difference is important in whatever you are measuring? And this is how the minimal detectable change and the minimal worthwhile effect can be seen together. So if you're measuring something and a difference of 0.5% is huge, it's a matter of life or death, right? But the minimal, that's your minimal worthwhile effect. But the minimal detectable change that this, whatever machine you're using, is 0.7%, is this going to work out? No. So this is a great way to see these two together and understand their applicability, okay? Their application, actually. All right, so obviously we'll have an international system that in some cases not very helpful for Americans. For example, in cases of when we're using kilograms, kilos, or meters, sometimes, you know, it's even hard for people to figure out BMI because they have to take something in feet and they have to make it into meters, and something in pounds, and they have to do it in kilograms. So the more exposed you are to this, the better. But in general, there's an international system. Okay. When you submit your proposal, when you're writing your manuscript, you have to use that system. All right, so this is kind of, we're getting a little bit too much detail. Sensor is something that will detect that change. Okay, the amplifier will just make it bigger, or bigger in order to get detectable, and as it goes to the analog digital converter to be able to, this device to convert it. And from here, this conversion happens so it can go to the computer and software where we can actually, so we have, let's say, an electrical signal, it gets amplified so it can be converted into a number, and that number would be converted into something that makes sense, like another number that makes sense to us, so we can actually use that information. Okay, that's all I want you to say about that. This is an example. You see A, B, and C, right? Okay, range, the difference between min and max. Cool, cool. Sensitivity, change in output of the sensor for each unit change of whatever we're measuring. Okay, that's important. Resolution, you can get it, smallest change to be detected, response, how quickly sensor produces an output, and cross sensitivity, how sensitive the sensor is to changes in the environment. Okay, so if we take something to the field, what's going to happen, right? All right. I don't necessarily care about all this information. Just make sure you understand what a sampling rate is and sample period. That's it. Calibration. Okay. Spend a little bit of time here. Measuring known quantities and recording the output from the AD converter in a process of measuring the output of a sensor in response to an accurately known input. So we have some input and then we get an outcome. Okay. We'll have, if you go down here, we have usually functions, we have some input and we have an output, right? So in order for whatever we're getting, it goes in to get an output, which makes sense to us, and that's what we're going to use, we usually have calibration functions, and we need to calibrate a lot of equipment, a lot of times electronically, sometimes manually, right? Calibration can even be something as you have a Monarch bike. It's not electronic, right? Manual Monarch bike. Monarch bikes are the ones that we have usually in the labs, MONARK, Monarch. So you need to calibrate it in a way so 0 is 0, for example, in the very beginning, okay? So remember this function because we're going to use it in a little bit. This is the slope, Okay, I'm not going to go a lot into math, and that's some adjustment to 0. Okay, okay. This is a curve. So here, as you can see, this is what we're going to put in here, and this is what we're getting. This is the actual force. Okay, this is the formula. And that r squared, that pretty much tells us that, in simple terms, that the difference that we see in the input is explained by 99% in the output. So this is really good. Really, really, really good. Okay. When do we do calibration? Whenever something changes or whenever we use it a lot. Okay. Sometimes we'll do like monthly calibrations, but after 10 people use it, or whenever we move it, or all the above. I don't really care about this. This is has to do with calibrations that we usually do when we move something to the field. So we take a machine that we usually use in the lab, and everything's in control, and we know what's up. You know, up from the temperature to, I don't know, anything. So you want to take it to the field, and things are different. So you do some kind of bench calibration, then you do field calibration, and then you use them to identify if everything is okay, or you should expect some kind of error. Okay, so again, not a lot of information here. Sources of error. We have the span, which has to do with, if we go back, the span error has to do with this, with the slope. So there's an error in the slope for some reason. Okay, and the 0 that we'll see in a little bit has to do with the input. Okay, and this is two great examples of systematic errors, which we're going to talk a little bit about in a little bit. So span has to do with where is it? Slope, and 0 has to do with the input. Okay, so also we can have combined, which is a little bit more difficult to identify or fix. Linearization is not very popular lately. It has to do mainly with some quantities. It's not accurate to be measured on a linear scale. Pretty much, that's what it is. And hysteresis has to do with, for example, if when input goes up, output goes up, but then if input starts going down, output doesn't go down as fast. So we have some kind of hysteresis over there. And this is what's happening right here, for example. I'll have this kind of direction. Some examples that I don't necessarily, this is a 0, 1. So it can go this way or this way. Okay. Okay. I know it's a little bit too much, especially if you're not working in the lab and you use this kind of equipment. But the good thing about systematic error is that if detected, you can just change a little bit of the formula. You make that adjustment. Boom, you're good. You fix the whole thing. The random error is exactly what it says, random. Okay, we've covered that before. Systematic, it should be predicted. We should take measures against it. Random, we should, again, try based on our experience to try to predict pretty much everything, but it's random. Okay, not easy to detect, so not easy to fix either, because it's just all over the place. There's no system behind it. Right, so there's a thing called noise, okay? And it can be based on all this thing, and of course we don't like noise, and we're trying to get rid of it. There's another thing that we can use to fix random errors called digital filtering. So whatever is high above something, it passes. Whatever is low, it passes. So the band pass is a combination of high pass and low pass. So we accept everything that's over this and lower this, right? And then the notch has to do with a very specific thing to attack, let's say electromagnetic interference, for example. So it is, the notch is a way to filter something very, very specific. Again, too many details, in my opinion, in this chapter. This is a low pass, so everything that's lower, whatever is accepted. Again, too much. This has to do with the rate, the chains. Integration has to do again with the rate, but there's a different way to do it. The one is called trapezoid. I don't necessarily want to go there. It's a little bit too much. So that's it. All right, guys. So again, I'm stop sharing this, and I'm telling you from my notes right here that office hours tomorrow, okay, from 8 to 12:30. That's one. Synchronous meeting on Wednesday at 10. Okay. If oh yeah, I could say that too. If you are ACSM certified and you're looking from CCCUs, I don't know if you know what the brown bag series. I'm going to be speaking on Thursday, so you can Google that. You'll figure it out. Brown bag series ACSM. So you can watch the webinar and get those extra points. I'm going to be talking about mental toughness, obviously representing the Greater New York ACSM chapter. And what else? And you have to submit Group 2 city training, right? LO14 and LO15. I'm going to include all this information in the email that's coming out very soon. Thank you, guys. Have a great week. In the meantime, live intentionally. Now have